Hi everyone, welcome back to Civil Engineering with Amir. This is Amir here with another video on the topic of shear force and bending moment. In the previous videos, I showed you how you can determine the functions for shear force and bending moment of a simply supported beam and also a cantilever beam with a point load P applied at a distance A from their left support. Now in this example, we have a simply supported beam with a length of L. But this time, instead of a single point load P, we have a distributed load with a magnitude of W, which is applied over the length of our beam. And now we want to determine the functions for our Vx and Mx. Alright, let's see how we can solve this question. We know the first step in solving these type of questions is drawing the free body diagram of the beam. So this is our beam. I've already copied our load. We have AY here, we have AX, we have BY. This is point A and this is point B. The length of our beam is L. And now the next step would be writing the equations of equilibrium for this beam and determining these support reactions. So okay. We know we can substitute our distributed load with a single resultant point load, which is applied at the centroid of our distributed load. The resultant force for a uniformly distributed load is going to be the magnitude of our distributed load multiplied by the length of our distributed load. So the magnitude would be WL, and the location, which is the centroid of our distributed load, is right in the middle of our load. So we're going to have a point load with a magnitude of WL, and this is L divided by 2. And now we can write our equations of equilibrium based on this simplified beam. So in the x direction, the only force that we have is AX. So AX will be equal to 0. Similarly, in the y direction, we have AY minus WL plus BY equal to 0. So AY plus BY is equal to WL, and sigma M around any point along the beam will be equal to 0. We choose point A, choose this direction as the positive direction. So WL multiplied by L divided by 2 minus BY multiplied by L will be equal to 0. So BY will be equal to WL divided by 2. And now if you put this BY in this equation, you're going to have AY plus WL divided by 2 equal to WL. And this will give us an AY equal to WL divided by 2. And now we can substitute these support reactions with the values that we found here. So I'm going to copy this beam. AX was equal to 0, AY WL divided by 2, and BY also WL divided by 2. All right, now that we have the support reactions for our simply supported beam, we can cut the beam at a distance x and then draw the free body diagram for one of our cut segments. So step 4, so I'm just going to copy this and remove this part. This is going to be our Vx, which is downward. This is going to be our Mx. And now by writing the equations of equilibrium for this segment, we can determine our Vx and Mx. So step 4, All right, so this is our cut segment. And again, we can substitute this distributed load with a single resultant point load, which is applied at the centroid of our distributed load. So the magnitude of our resultant force will be W multiplied by X, and it will be applied in the middle of our length X. So we're gonna have a force like this, WX, and this distance is going to be X divided by 2. And now sigma Fy equal to 0. So WL divided by 2 minus WX minus Vx is equal to 0. So Vx will be equal to negative Wx plus WL divided by 2. Sigma m around any point along this segment will be equal to 0. We choose this point and we call it O. Choose this direction as the positive direction. So WL divided by 2 multiplied by X, and our moment will be in this direction, which is our positive direction, minus WX multiplied by this distance, which is X divided by 2, and it's going to be in this direction, which is in the opposite direction of our chosen positive direction. That's why we're using the negative sign. Minus mx will be equal to 0. And this will give us an mx equal to minus wx in the power of 2 divided by 2 plus wl divided by 2 multiplied by x. Now that we have determined v and m in terms of x, we will be able to draw our shear force and bending moment diagrams. So at point A, we had an upward support reaction with a value of WL divided by 2. So we'll go up. This is WL divided by 2. And then we're going to have a linear function with a negative slope. And at x equal to L divided by 2, our shear force will be equal to 0. So it will be like this. And then at point B, we had a positive shear force with a magnitude of WL divided by 2. So this is negative WL divided by 2. And your moment function is a quadratic equation. At x equal to 0, your m is equal to 0. At x equal to L, your m is equal to 0. And at x equal to L divided by 2, you have a positive moment with a magnitude of WL in the power of 2 divided by 8. WL in the power of 2 divided by 8. It's L divided by 2. And your quadratic function will look something like this. This is L divided by 2. So these are how your shear force and bending moment diagrams will look like for a simply supported beam with a total length of L and a uniformly distributed load with a magnitude of W. Thanks for watching this video. I hope you found it helpful. If you like this video, please don't forget to press the like button. If you have any comments, suggestions, or feedback, please feel free to write for us in the comment section. And finally, please subscribe to the channel if you haven't already. Thanks again and see you in the next video.